also showed you how you locate them, and you can actually, in ETABS, you can switch on the axis show, and it will show you all the axes on every member. So it's important that you switch on the local axes one time before you do the analysis and make sure that they are where you want them. Also use the extrude view to see that the beam direction dimensions are correctly oriented and properties are correctly oriented. So this 1, 2, 3. So normally, now we are used to drawing like this one, but in ETABS, it's like this, because depending upon whether you look this way or you look this way, this will change. So some people put 1, 2, and 3. Some ETABS puts 1, 2, and 3. 1 is coming out, right? So that's why you sometimes transferring results from one program to the other program, the sense is changed. Direction, like +3 becomes, +2 becomes -3, and so on. So I have to be careful on understanding the results and the axis. So global and local axis, CSI, ETABS, they have a lot of ways to define and look at them. So whenever you go, you can see how they're oriented. You can also specify them, this one. So why it is important? Because when you apply forces or on the members, then you have the option to apply them in global axis or local axis. So if you apply them global axis, the force, vertical force could be here, but local axis, if the member is like this, you want to apply it like this. So wind is applied on the local axis, gravity is applied on the global axis. So that's why you need to understand where the local axis is, how to apply the load, and how to set them. So frame coordinate system, once again, various default, like column is like this one, beam is like that one, and then inclined. This is the difficult one. When the member is inclined, you must specify the angle on how it is placed. And it's very confusing to locate an inclined member. This is let's say this one here. So it could be like this, it could be like this, it could be like this. So you have to make sure that you orient this one correctly in members which are inclined. Forces and moments were always reported on local axis, not global axis. So you will always get the results of a analysis, member results on local axis, local M2, M3, V2, V3, and so on. And so you should know where they are. Normally for beams, we worry about M3 and V2 in ETABS and torsion. Now, these are the various combinations of degrees of freedom for various applications. There is a book called, you can search Matrix Analysis by Gary and Weaver. That was the first book, really good book published about this stiffness method, stiffness matrix. It was published in maybe 70 something. The good thing about the book was that at the end of the book, they had 6 program code in Fortran that you could just use directly. They had written the Fortran code for 6 type of programs. First program was 2D truss. Second program was 2D beam. Third program, 3D truss. Fourth program, fifth program, sixth program. So they had 6 separate programs dealing with each 2 degrees of freedom, 3 degrees of freedom combination, ultimately coming to the space frame. Because at that time, saving memory and all of that was so important. So Microfiche, AIT's first program, also decided to have 6 modules, P1 to P6. So P1 is here, P2, P3, P4. So they said they will follow the same thing. So there were going to be 6 modules. But after P2, then things start to change so much, people didn't care about anymore. And now these days, we always have this situation, and we downgrade to the others. So this is always implemented. But now we are going back to Eagle Eye, and we want to revive this idea again, because this is the way to understand things better. You clearly know which degrees of freedom are being considered. You can see the metrics being formed. You can see the metrics being solved. So in Eagle Eye, we plan to go back to this idea and implement them one by one, showing each thing clearly. Now we come to surface element, the next level, 2D element. 2D element means the two dimensions are specified, and then thickness is a property. And these 2D elements can be, now once again, based on the degrees of freedom active, can be categorized into two groups. One is a plate and one is a membrane. And when you combine them together, it becomes shell. So once again, people started with even less than this one. This is 3. This started with 2 degrees of freedom, plane stress and plane strain problem. Then came plate bending problem. Then came the membrane problem. And then finally, shell problem. So this is important, and I will show you why. So ETABS will still has the option to choose between these 3 elements: membrane, plate, and shell. And a lot of engineers choose the wrong one or not the correct one. And when I used to do seminars earlier, this was one of the most common questions I will get from the engineers: which element I should use for what purpose? So I want to make that clear. So this one, like I said, is plate bending. That means this element has no in-plane degrees of freedom. So you cannot calculate anything in its own plane, only bending. So going back to, okay, this one. So you can calculate the bending like this, but you cannot apply any tension or any force in the plane. So if it is a wall, it won't work. If it is a beam like this, it won't work. It will only work when force is applied perpendicular to the member. Membrane is opposite. It will only work when the force is applied in the plane of the element. It will not work when you apply perpendicular to so they're opposite to each other. So when you combine them, naturally you get the full shell behavior, which has both in-plane and out-of-plane forces. So shell is complete. And you can say, oh, I can use shell all the time. Of course. Now you can say that because you're rich. We're talking about the time when each degree of freedom was very costly. So you could not use shell. If you use shell, you can only use few shells. If you have a large problem, you cannot, because memory of the computers, hard disk, everything was so little. Okay, this one here. So first of all, the shell or element has 4 nodes. Typically, the standard shell element or plate element or membrane element has 4 nodes. So this is the most confusing part between ETABS and other programs. ETABS numbers them J1, J2, J3, J4, right? Like this one. So they are going in this direction. But many programs will do J1, J2, J3, J4. So depending upon how the programs are written, and the reason people used to write that 1, 2, 3, 4, easy to generate numbering. Just keep adding 2 and then you're generating. So it was easier. So people start to do like that. But in finite element, we must have a direction of the numbering, because that will decide on the orientation of the element. So if you number it like this, 1, 2, 3, 4, that means you are going like this, and this one is your z-axis, 3 positive axis. If you number 1, 2, 3, 4, then your z is downward. So positive direction of the face of the element or the vector perpendicular to that is decided on the order of numbering. So if you change the numbering order, it will point the other way, and the sense of all bending moments and shear forces will change. So that's why it's critical that if you're doing the manual numbering or manual drawing, we must do the correct way. Click, 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 like that. If you do this way, it will be reversed. And then sometimes we need triangular elements. And many programs have triangular elements because sometimes the mesh is like this, that you cannot only use 4, you need 3 nodes. So in ETABS, normally they don't have triangular elements, so they just converge 2 points here. Now, also look at these faces. So this is phase 1, phase 2, phase 3, phase 4, and phase 5. So 5 phases also created from an element. So element is supposed to be like paper. It has the plane it has no thickness as such. Thickness is a property. It's a two-dimensional element, not three. But when you put the thickness, then it will be like this. So thickness is virtual. But that thickness becomes very important because if you apply a load on the side, that face will take the load. So it is converted back into in-plane forces. So understanding of this element is important for analysis and also for applying forces and also for applying pressure on the edge, on the foundation. Let's say you use it as a footing, then this face will be in contact with soil. So you need to know which face is that. And so top face, bottom face, soil is here, there's no soil here. Say this side we have a soil, here we don't have a soil. So you need to apply the forces, attach the springs very carefully. So that's why understanding this diagram is critical for local axis and for faces for applying load and for checking stress. And now look at this one. I use simple model here, and this one I assign shell, this one I assign plate, and this one I assign membrane. 3 different elements, and then I mesh it further, and then I apply a load at the top. You can see here that this membrane, this load just went through because it has no bending stiffness. So the load, the structure become unstable, and then load just went through the plate. Even though it looks like that it is working, it's actually analysis-wise it will not work because this is membrane. Plate can carry that load and shell can carry that load. And this, sometimes engineers do not understand what happened. I modeled the slab, and then no load is transferred to beams because the load applied here cannot go anywhere. There's no stiffness in plane. So that's the first rule, that if you're using out of plane forces, you should not use membrane. But the confusing thing is that ETABS used to use membrane in the beginning to model the floor. But then they will transfer the load manually to the beams. Before I showed you earlier, the geometry-based load transfer. So they will use the membrane only to make the stiff floor in plane, but they will use manual load transfer for the beams, but will not apply the load to the membrane. Now let's put it the other way. Let's say we have a wall. I use shell, plate, and membrane. Now when I apply the load, the plate just deforms a lot, fails immediately because plate has no in-plane bending stiffness. But shell, of course, is always work and membrane works. So which means when you apply the force in the plane here, then it will be membrane and shell will work. Plate will not work. If you apply the load here, then plate will work, shell will work, membrane will not work. Okay. So of course, now these days, people don't even care about that, and they just use shell automatically everywhere because it covers everything. Now we come to solid element, the last one in the hierarchy. Solid element is a true three-dimensional element. That means it connects, it can model all 3 dimensions. So we have like a brick. So some people call it a brick element. But the nodes don't have to be at the same height. So each node can be different height, different location. So you just model a volume of using this brick element, a brick or its solid element. So this could be like this one. It could be a transition element. It could be a wedge element, tetrahedron, pyramid. So these are all variations of the same solid element. Some people have even 20 nodes. So some people have, let me go back. Shell element, typically we say is 4, but some people use 9 elements, 9 nodes. 1, 4, 5, 6, 7, 8, and 1 in the middle. So they can model curved surfaces with fewer elements. But now, like ETABS don't have it. They just use more elements because now memory is not a problem. So instead of using few elements of 9 node, they use 4 elements and they still get the same results. Same is true for solid. So this is 8 node, but some people have 20 nodes in between, 11 nodes, and so on. Many nodes, multi-node solid element. But once again, SAP and ETABS people decided to use just one 8-node element. So in number of elements, SAP is probably the least number of basic elements. So they spend more time optimizing those elements than rather than trying to create more elements, because as you add more elements, you get into trouble of meshing, you get into trouble of connecting, you get into trouble of getting the results, you get into trouble of compatibility. So they decided not to go that way. Just very few basic elements. One frame element, one shell element, 4 nodes, one 8-node brick element. Advantage is that they can use one shell element below, one shell element top, connect them together, and becomes a brick. And that is so good because they can extrude this one here, just extrude, copy this shell here, connect together, and you make a solid. So they can easily convert a shell model into solid model by simply extruding by a number of layers called extrusion. So that is very, very good because you can take the cross-section of a beam and then just extrude it, and it becomes a solid mesh, right? So this allows them for, same is the case, I will show you later, how from point to line, line to area to solid is one continuous extrusion. Okay, now we come to the joint restraints, boundary. So we have talked about the 0 degree element, we have talked about 1 degree element, we have talked about 2-dimensional element, 3-dimensional element, and finally now boundary. How do you lock the structure? Because our structure cannot run away. So it must be locked somewhere. At least one restraint has to be provided. You try to model a structure with 0 restraint, it will be unstable. So at least one restraint needs to be provided. In fact, more. So this is the way that you provide it. So you take any node and then you can fix some of the degrees of freedom. Here you call it a hinge. You fix 3 degrees of freedom. You call it roller, 2 rollers and 1 vertical. Similarly, you can also attach springs. And this is a powerful tool. Instead of using free or fixed, you have partial support. So this can model soil and other things. So you put springs there, you can fix there, and then you can have rollers fixed and this one. And this is what I told you. You can rotate the roller, you can rotate these things to get the effect that you want. This is the computer that I used in my undergraduate to write my thesis project. So this is called ZX81 from Spectrum. And it was in 1981 that they launched it, 1981. It has a soft keyboard and it comes with 1K memory, 1K. So you only can store a few, maybe 30, 40 variables. And then I bought a 16K extension that you put here. So it became 16K RAM module. So total is 17K. So I used this one to write my first frame analysis program. So you can imagine how much this memory has to contain the program and also has to contain the data for the model, because that's the only memory you have. So you have to write the program in the most efficient manner because each character uses 1 byte. So if your variable is A, is 1 byte. If it is ASL, it is 3 bytes. So you have to keep your variables within single letter as much as possible. So keep reusing the variables. And I have the manual somewhere here also. So this is the one that I used. And it has no screen. It has no external. This is RAM. You cannot save anything on it. If you switch off, it's gone. So then it came with this one. Audio cassettes. You connect this audio cases to tape recorder. And then you save your data on the audio tapes. So when you play that back on a normal, you will see it because data stored in audio signal. So this is the audio tape, which contain data from the computer, converted from digital to analog. So saved as analog, and then you convert back from analog to digital, and then you get it back. And then there's no screen. So you take a small TV, and then you connect to a 12-inch TV, black and white. And then so you build your computer piece by piece like this. So this is the starting of the computing. It's so unfortunate that this company that started everything just disappeared. They did this long time before Apple or anybody came to market, or Microsoft or anyone. But their innovation, they just did not survive. Second one, I want to show you this one. This is compact. It's 20 years ago. First tablet that you can get, and you can actually write on it at that time. And this one I used for my doctoral thesis. Did most of my work on this one. And this you can detach and you can carry it. And I used to put it in the plane, and people will come and watch. What is this? Because I'm writing on the screen, and I have a laptop with me in the plane. No one can imagine a laptop in a plane in 1999 or 98 or something like that, right? And then you have the keyboard, and you can just disconnect this one. So this was once again, it did not survive. It was long before iPad, long before Apple. They already had something like this. Surface is now, you see all these things now, but it was there. I have one more thing. They didn't show me the Palm Pilot, where you can write on the phone, also 25 years ago. So these companies, we don't know about them, but they did all this thing long time ago. Okay. So coming back to the memory thing, so we used to work on something like this. This had 16K memory, and the mainframe in our university, IBM 1130, also had 16K of memory. So the mainframe in the university and this computer had the same memory, and we make a joke about that, And people used to come to my room to look at this. It was the only in the whole university of something like this. But the point is that we used to work in an environment where saving every byte, we count the bytes, how many bytes this program will use. So degrees of freedom, everything was so critical. You have to fit your problem to the tools you have. Unfortunately, now we don't understand or value all those techniques. But they were very good modeling techniques because they were efficient. So that's why now programs are still not efficient, because the computers become very fast, but we just try to mesh too much. We should be solving bigger problems. We are not solving bigger problems. We are solving the same old problems with unnecessary meshing, unnecessary elements, unnecessary details. All right. So now what are the challenges in modeling? My question is, can you model this simple structure completely? And I still challenge you. This is a challenge for anyone who thinks they are very, very good in SAP, ETABS, or whatever you use in any finite element program. You still cannot completely model and analyze this structure with all the sophistication that you have. Okay, so we want to analyze this for gravity load, lateral load, dynamic impact, thermal temperature changes, everything that can happen to this normal, right? Wind coming from here, earthquake shaking it, wind coming from this direction. It's just simply supported. It's not connected. Remember that. So it can slide off. It can topple. It's not connected. So it can, if the force is large, it can actually fall down. The wall can break. We don't know wall will break first or beam will break first when you have had lateral loads. So everything is open. It is as it is. Okay, it's a masonry wall. So deflection, stresses, cracking, stability, failure. Of course, on simple side, you can just do hand calculations. You don't need anything else. Obviously, you can do simple calculation, calculate bending moment, calculate shear, calculate design. Everything can be done by hand. Stability can be checked by hand. Sliding can be checked by hand. But the question is not that. The question is, can you do it on a computer with correct modeling? That is the question. So the first thing is that you create a frame from this one. First thing you could try is that you can create a frame, call this as a column of this cross section, and then you put a line, and then you call this a column of this line, and then the beam center line is over here, and the beam section is like this. First problem is that the center line of the beam is not at the top of the wall. It is away from the wall. So if you want to now, please watch this carefully because it's very, very important point. You might want to say, okay, I'm going to model this beam like this and apply the load. That is the beam over there. But your supports will be here and here, not where the actual wall is resting, because your supports are at the ends of the beam. But the beam is connected at the bottom of the beam. So you are just missing that whole offset of the beam from this one. So if you do that frame model, where do you place this beam? Will you connect it to these 2 points? That means you have effectively brought the beam down, physically not correct. And if you keep the center line there, what do you do with those portions? What is that? So if you want to create a frame out of this one, you think that you can create a frame like this one. That's the beam, that is the wall. The wall finishes here. Beam is here. What do you do with this height? This is the first problem is that your physical structures, supporting and connections are not at the same location as the center lines of the member. Challenge number 1, traditionally, this would be a problem. Rigid zone, yes, correct. But suppose your software doesn't have rigid zone option. What do? You only have this program. Yeah, you add another element over there and increase the stiffness to be very large. So create your virtual rigid zone. So you put another small element on top of the column, not shell, frame. We're talking about frame. First is frame element. You cannot use any other element. First is a frame, centerline frame model. You cannot deviate from centerline frame model theory because that's all I have in my software. I'm trying to bring you back to this level, that in this program, all I had is a frame analysis, 2D frame analysis program. What will you do with that? So the first thing is that you need to create some kind of a dummy element and assign a large properties so it will act as a rigid link over there, right? But the first thing is you need to recognize that there is a problem here. You cannot just use centerline without this correction. That's what I'm trying to tell you, that you have to think about that there is a problem. I cannot just use simple frame because there is a offset that is missing. Okay, I'm talking about the challenges. Then you say, okay, fine, I will. And second one is that you can say, okay, I will model the column by a shell element better than that one. And I will model the beam by frame, same problem. Offset connection, still issue, right? Third option, you can say, okay, I will solve the problem. I will model the beam by membrane, and then I will model the wall by shell or all shell element. So this is one improvement, that your model now becomes closer to reality. Now you don't need to create any artificial things. But the problem is now you will not get any bending moment in the beam because shell elements will not give you any bending moment. Shell elements only give you stresses. They don't have in-plane bending moment. So that means then to calculate the bending moment to design, you will have to do some kind of integration from the shell results. So you solve one problem, but now you create another problem. Second problem is that this connection between them is actually rigid, but your beam is just resting on it, not connected to it. But here you connect it. How can you have a finite element where the connection is just resting there? It can lift off, it can slide, it can rotate this way. So you can see that even though you get a full shell model, looks very nice, but you still haven't solved the problem of the basic connection. The other problem is that this is a brick. How do you calculate the shell properties of a brick masonry wall? This is not concrete. Each brick is individual. Each brick can separate from each other. So you are trying to represent it all by a single shell element. What about all the bricks inside? What about their joints? You didn't solve that problem also. So then we say, okay, let me go to solid element. Let me use solids for everything. then you put solids everywhere, you put solids everywhere. Now your model is very close to reality, very close to reality. And if you keep refining it, you can use one brick, one solid element for each brick also. But still, the connection between them is still going to be rigid. Still, that problem of the sliding joint and free resting joint is not solved. So now you can see that a very simple beam and placed on wall, even the most sophisticated solid mesh is not going to solve everything that we want to do. So now you can quickly see if you start thinking about modeling and think deep enough, every problem will become highly complex and you will never be able to solve it. So, which means we have to make some educated simplifications, but at the same time, we must have the knowledge and ability to go all the way to the final possible way. All right, let's go forward. So now we know that, okay, at least these 4 models are possible. Now, these 4 models are possible, but here you will find the problem between the meshing, not matching, and this and that, and solid. So we need to do a lot of careful meshing to make sure that things are connected and aligned to each other. Otherwise, actually, this model is not correct because solid nodes are here, this node is center, they will not connect. You have to have matching nodes to connect. So that means you have more refined meshing is needed. Also, you need more lengths here to model the wall thickness, connect them together. So the meshing will become very challenging to match everything together. So I created these 6 models from that one using SAP. So this is a simply supported centerline model. I just extrude it alone, resting on end supports, no walls. So I remove the wall and I just model the beam and put the restraints at the end. This one I modeled everything by frame. This one shell, this is framed, but it's not correct because it goes down. As you can see here, it's not at the top of the wall because I use centerline model. Then I say, okay, let me correct it. I move it to the top. I use this also shell. I put it on the top. And this one, then there are different models with different kinds of connections and meshing to connect them together. And then I use solid element. You cannot see the mesh. I use 3 solid elements to match with the thickness, not match with the thickness, and things like that. And finally, I get a model, 6th model, which is everything is matching. All the meshing is accurate, but it's still connected. I still could not model the sliding behavior, overturning. It is still connected. The beam will never fall down this direction. It should fall down, right? It will never fall down because it's connected. It will never slide off the wall because it's connected, no matter how much load I apply. How much temperature I apply, it will expand, but will bring the wall together. But actually, that's not true. When it expands, it should expand alone after some time. Slide and then expand. So all of these issues in these 6 models, even with all the refinements that I could do, still not done, right? So the point is you must think about the behavior. What is it that you want to capture and make the model accordingly? If you just want to get the bending moments in the beam, first model is very good. Anything more than that, then each model will give you more, but not all. So what a good model should do then? Where should you draw the line? Where should you stop? Represent materials realistically. That means right now I'm just using E value. I'm not even talking about nonlinear models, and I'm not even talking about failure and cracking. None of these models can give me cracking. None of these models can give me true deflection. None of these models can give me ductility because solid elements do not have nonlinearity. So I cannot capture any of those. Everything is still linear and gross, right? So with all these refinement, I'm still far from real behavior. So that's why it's important to see what do you want. Linear elastic is a starting point, not the end point. So normally we start with linear elastic as a starting point to set something, and then we will use that to go to the next level and next level. Represent geometry accurately. Centerline assumptions introduce error. You can see now. Know where to modify, when to modify, what to do with this centerline problem. And there are now software have become very intelligent. They keep giving you better and better options, but that should not relieve you from thinking. Just automatically rely on the program, it will fix the problem for me, is no good. So you should know what the problem is. What did I do? What did the program do to fix it for me? And what can I do to further improve it? Represent connectivity properly. Beam resting on the wall should not be rigidly connected. That connectivity should be correct. Right now, it's not correct. So third is this connectivity should be proper depending on what we want. Represent excitation reasonably. We didn't even talk about the wind, to how to apply the temperature variation, how to apply the seismic ground acceleration, all of that stuff. That's still, we didn't even think about it yet. Even our model is still developing. Capture invisible behavior. This is very important. Capture that invisible behavior of sliding and falling off and toppling. Those are invisible behavior. Try to capture them. Friction, uplift. Understand the computed response. So, like I said, shell element does not give you stresses, but you don't need bending moment. So you need to then do some more computations, put some section cut, integrate the stresses to get the moment back. Solid element also, you need to integrate the stresses to get the moment back. And make appropriate design decisions. If you cannot solve everything, then make a decision based on your judgment. This level, we didn't have anything, but we still designed everything. So many things we designed by making proper design decisions without having enough analysis output. But design decisions have to be made anyway. The people at the site will ask you how much reinforcement you want to put here. You have to answer that. You have to make the drawing. So as I mentioned to you in the beginning, I would try to do the design without calculation first. Always. Get it, understand, put all the reinforcement, design everything, no calculations yet. Then go back and do some calculations and cross-check important points. Keep the rest over there. Use my judgment. But unfortunately, now that sense isn't there. We just rely on the computations too much without thinking. That's why I want you to think from the fundamentals for the basic problem like that. So linear elastic assumption gives you simplicity, superposition, stability, code compliance, and it is sufficient for service level. When loads are not too high, it is fine. Like the wall is not, it's not sliding off, it's fine. It's not falling down, it's fine. It's not breaking, it's fine. So as long as loads are small, deformations are small, within service limit, most of the time it will be fine. That's why linear elastic analysis works. But it doesn't work earthquake. It doesn't work in cyclone. It doesn't work when things get really, large. Temperature, fire, something hitting the wall, things like that. So elastic linear assumption, what it misses is material nonlinearity. We already know that. It misses geometric nonlinearity, contact and separation. We already know that. Friction and sliding, hysteresis and damping, and cumulative damage. All these things are missed by linear analysis. So here you can see easily that we could not model this. The effect that it might slide off. One important thing, note here, this detail. When this beam rotates, it does not rotate at the center line. It rotates at the edge. When it deflects, it will put more load at the edge of the wall and it will lift up like this. Not at the center, as we assume. So this is important distinction between physical and centerline model. Centerline is assuming it will rotate at the end, this is free, but no, it will be at the edge of the wall. So which means that there will be certain lift off and then push on the wall also. So those kind of things you cannot capture by centerline models anyway. So the connection problem is a serious one here. As you can see, this is much more important in bridges because in buildings, normally things are connected. The previous example is more like a bridge where things are just lying there, like a bridge girder on a support. and things are all disconnected and still transferring forces. So the connection problem, and also in steel, sometimes it's like that. So friction and sliding, falling off the wall, free rotation at the edge, loss of contact area, lateral stability, normal force variation, all these are issues that will come for the disconnected areas, not the one which is. So buildings are very, very susceptible to these problems. So that's why precast buildings, this kind of analysis is critical, because things are not connected, or they're connected after placement. So during construction, they are in a dangerous situation. But just to tell you the solution, this is the solution to all those problems. Behavior elements. So far, we have been talking about elements that represent physical geometry. The invisible behavior is represented by invisible elements, like this one, which is these constraints, springs, links, dampers, isolators, and hinges. None of them is real. They all represent behavior. So you can combine the geometry, physical geometry elements with these physical behavior elements to complete the system. So this is what I was trying to reach at. So we'll talk about these behavior elements in the next course, all of them, because they are your solution or answer to the problems that you could not solve only by physical modeling. So we talked about the connection problem, and I told you that the things can fall off, can be disconnected, can slide off, and we cannot capture any of that by using the traditional elements, frame, and all of that. So we talked about that, and then we say, okay, all of this requires something more. And we said that, okay, these elements are the one that we can use to capture the behavior. And I mentioned briefly, so this one is the most powerful thing in ETABS and SAP that you can see, which can help you to solve any problem, almost any problem that otherwise cannot be solved. So if you can understand these links, you can literally solve very, very complicated problems that otherwise think are impossible to solve, because you can break down the whole structure into a series of links, nonlinear links, and then you can give whatever properties that you want, whatever behavior that you want, almost anything, even very complicated one. But the problem is these elements are way too complicated. If you really get into that, I will not have time to discuss in detail, because this is not SAP, this is ETABS, and we are just. But what I want you to understand is that whenever you face a problem that you cannot solve by any of these standard methods, and you want to go into further detail, then you should start thinking about using these nonlinear links, or links, linear and nonlinear. In general, a typical link has two nodes, two joint I and joint J. And within that, you have actually 6 degrees of freedom connecting those two joints. So each degree of freedom, axial shear 2 kinds, bending 2 kinds, you can use, and torsion, you can separate them into 6 separate connections between one joint. Each of this connection, each of this degree of freedom can be independently defined as linear, non-linear, damper, friction, whatever you like. So which means that you can create very, very complicated, comprehensive, complex connection between 2 points. Normally, when you make a frame, it automatically connects all the 6 degrees of freedom together rigidly. Here, we separate that node into 2 parts, and then we say, okay, this node, let's say, this is very important for you to understand. Normally, when you draw something like this node, which I presented like this to you last time, is a single node connecting these elements. And this is rigidly connected. All degrees of freedoms are continuously going through this one. What you can do is that you can say, no, I'm going to use 1, and I'm going to use 1, very small distance, and I'm now going to reconnect them the way I want. one by one. Each 6 degrees of freedom, you can disconnect them all and then connect which one that you want and how you want. And that's the power of these links. So you can put one link per degree of freedom, or you can put one link with 6 degrees of freedom together. So it's unlimited. You can provide several links between the two nodes, and each with different behavior. Or you can connect one link and then assign different behavior to different degrees of freedom, depending on how you want to do that. So this power of this link is the one that gives you that, what I'm saying, behavior. So, and then inside, you can then, after that, you can do damper, spring plus damping in a series. You can put what is called gap, spring and a gap, and then you can put what is called hook, a spring and a hook. So the spring is used when you run linear analysis, and the damper when you do use dynamic analysis, and gap and hook when you run nonlinear analysis. So now you can specify, going back to the problem, you can specify, for example, the most interesting example of this application will be a very simple cantilever with a wall here with a gap. Let's say 10 millimeter, and you have a load here. So this is a classic example where you can use the gap element. So what will happen is that if you apply that load on the P, the cantilever will deflect freely in linear elastic manner. But when it hits the wall, it will no longer, let's say the load is also here, W. So when the cantilever deflects by 10 millimeter, then this gap will be closed. And then after that, the load will be transferred by the stiffness of that wall underneath. So that means now it has a two behavior before the gap is closed and after the gap is closed. And this is the key to most all of them, that you have a nonlinear portion and then you have a linear portion. So then you can model what will happen to this beam as a cantilever and as a prop cantilever in the same run. Clear? So that's the way to handle all of these problems that I talked to you about earlier that you otherwise could not handle. So this is very simple. There are many more to this one. So then on top of that, other behavior elements are constraints, springs, point springs, line springs, area springs, soil springs, many kinds of springs here. And then you have the links, linear. So each degree of freedom can be, in each direction, can be fixed or fixed stiffness. This can be nonlinear, gap, and hook. It can be damper, or it can be a combined hinge, nonlinear hinge for yielding. All of these are special behavior things that you can do on top of your model, which are not handled by conventional modeling approaches. And all of them are very useful depending upon what is it that you want to do beyond the typical example of free and fixed. And this one, gap, some data for the gap I showed you. So each one, when you open, you will have to provide some gap, some stiffness, effective damping. So this is a combined gap and damper, like I showed you, and stiffness and opening. So you can specify what's the opening in the gap. This is a hook, same way. This is a damper, multi-plastic, multilinear plastic with damage and all, friction pendulum. So these are further examples of nonlinear things, and we can go on and on and on. I think we can, this is so much data, so much things to be done in ETABS and SAP for each one of them that I don't even understand half of it. There's so much data there, so much complication. But the point is, if you understand and you know what you have, then you can go on doing very, very deep modeling with that one. So base isolation, tune mass dampers, seismic gaps, transfer beams, soil and foundation interaction, all of those can be handled by using those special behavior elements. So and even with all of that, there will be a limit when ASAP and ETABS will not be enough. And you may want to go to another software. Normally in practice, it's not needed, but research, yes. So if you For example, frame, shell, solid, nonlinear links, nonlinear. If you have exhausted everything, is no problem. Then general contact mechanism, surface to surface sliding, not point to point, but surface to surface. That you're not modeling just a node with a two connection, but full surface contact, you cannot handle. Then fracture and crack propagation, you cannot handle. Micro level masonry joint modeling, the mortar inside, and all of that we cannot handle. So when you go to that level, then you need programs like ANSYS or other programs. So that's mostly used for research or OpenSeas in some cases. So as long as you remain at the element connectivity level, is fine. Once you go inside the material, you get into trouble. Then SAP and ETABS are not designed to handle it well, that well. Okay, go back to now some practical guidelines on how to make the modeling, the 5-6 modeling principle. You remember we started with 4 principles for tall building system selection. These are 4 principles for making a good model. Number 1, model the behavior, not the geometry. So this is very important distinction. And this is a problem right now with most engineers at this point. Because previously, ETABS or SAP was a separate program. AutoCAD was a separate program. So whatever architects do in AutoCAD is their business. When you come to SAP, you have to make your model by yourself. Every element, every node has to be drawn by you. So you will choose to draw only things that you need for the analysis, and you will ignore things that are not related to you. And you make a very clean, minimal, proper model, just enough for you. But now they have import function from AutoCAD. So when people import the AutoCAD drawing or model, they bring everything in. Small opening, small pipe thing, whatever is in the drawing, they just bring it in. And then they try to create a structural model from that information. So a lot of the unnecessary geometry comes in and behavior is missed. And they just use auto meshing, auto connection, and do not understand that what they brought in was not useful, not correct. Structural model is different from architectural model. And that was originally a manual, clear decision by the engineer. Now it's mostly automated. And that's why the problem comes. So you have to be careful not to try to model every beam, slab thickness variation, MEP opening. Don't try to find every small thing, because there's too many things in the architectural detail. Small slope ramp, for example, there's a floor. It's flat, but in architecture, they made it slightly inclined for drainage or whatever. And if you now just change your model from flat floor to inclined floor, you will be in huge trouble, because ETABS doesn't have sloping floor. So it will create so many stories and ramps, and it will just complicate your problem for nothing. And you could have easily ignored that small angle and make it flat. So things like this can mess up your model. So be careful with that. Model what governs the structural response you're analyzing. Just focus on what is it that you're doing and why you're doing that. For lateral load analysis, cores, frames, outriggers, and matter most. For gravity load, floor system, and lateral load paths, and gravity load paths matter most. That's why before ETABS for lateral was separate program, SAFE for floor was separate program. People will concentrate on one floor in SAFE. They cannot see the rest of the building. Perfect. They only concentrate on gravity load resisting system. And then when you go to lateral load analysis, they don't need to worry about the floor details. They just model the primary things and be perfect. Now ETABS can do both. So now people make 40-story building with very fine mesh and openings and all, and then they say they cannot run the program, or it's too much data, too much output, because they didn't make the decisions to just model what they want. So for your project, you must make sure that you make the right decisions on modeling. Don't try to just model everything just because architect has shown it. Ask yourself a question: do I need it in my model? And does it a behavior or is it an element issue? Then overly detailed models can be obscure rather than clarity. So they actually hide the clarity, then make it better. So this is very important principle. Don't focus on the geometry, focus on the behavior. 2D versus 3D. Obviously, now these days, we automatically think 3D for everything. But sometimes 2D models are very good to understand what the behavior is. So even if you do not have to, try to make a simple 2D model of the building, 2D model of some things, so you can understand what's really going on. Because 3D is complex, but 2D is clear. As human beings, we are very good at looking at paper and drawings and 2D information. So that's why I try to create check models in 2D. 3D models required when torsion is important. Full 3D models in ETABS standard for all tall buildings today, but it wasn't the case. Simplified 2D models are still valuable for checking and understanding. So please read these things very carefully. Each step here is useful. Model complexity must match purpose. This is very important. You have to think why you're doing this. What is the purpose of this particular analysis? Is it a preliminary design for checking sizes, or is it the final design to submit to the authorities? Why am I doing this? Am I checking the stresses? Am I checking the bending moment? I'm checking the deflections. So if you're just checking the deflections of the overall drift, you don't need a lot of things on the floor. It doesn't matter. If you're designing the floor, then you need the details of the floor and openings and stuff like that. But if you're checking the natural period of the building, floor is not even important there. It doesn't matter. It won't alter any of the modes because they're global. So no need to worry about so that's why purpose of the model and the model should match with each other. So code check, simplified elastic models with code load is sufficient. Performance-based design, nonlinear, preliminary design, avoid excess refinement, iterate rapidly, make a simple model, run many times, check things, fix things. Once you're comfortable, then add details. Don't start with the final model right away. Start with a very simple model, minimal model. Like, for example, floor outline just is enough to start from the overall behavior, and so on. Then final design, increase detail at critical elements and connections where you need more details. Match model fidelity to decision being made. So make sure that the model's depth and width is matching with your decision that you're trying to make. As you know, as I mentioned before, AI also, answers are there. You have to have the questions. If you don't have the right question, you don't know what we're looking for, and all kind of answers will come up. So make sure that you have the right questions before you do the analysis. Always have a check in mind. Before you do the analysis, you should also already know the answer. If you don't know the answer, you will never know what you're getting is correct or not. And as we were talking about just now in the office, use of the AI for problem solving or coding. If you don't know what you're looking for, you can never reliably check what you got. So the answer should already be there. For example, drift, like time natural period. You're looking for a natural period, but you already know it cannot be too long, cannot be too short. It's going to be in this range. If you're looking for drift, you already know drift cannot be 7% or 0.1%. It has to be something you already. So the answer should be known beforehand, before you done the analysis, and you're just confirming within that range. So if you have no idea what you're looking for, no point running something. Use simple models to verify. And if it is, like I said, if the ETABS result is 2 times your estimate, something is wrong. But you have to have the estimate first, and you have to have a good estimate. So it cannot be so wrong. Analysis should not be. So if you estimate analysis at too much, either your estimation was not good, you don't know what you're looking for, or the model is wrong. So which means that we must develop the design sense before that. Period, base shear, drift should be expected range. So you should know base shear cannot be more than 5% for a tall building, for example. Natural period cannot be this. So you have to know all these numbers beforehand. Garbage in, garbage out, of course, we always know that. Okay, so coming back to modeling in ETABS. So in ETABS, normally SAP and ETABS workflow is like that. We start a new model. You already know first of all, we try to model the stiffness. And then we define materials, sections, and they will define the stiffness for and then you have then area loads, load cases, load combinations. Then you write the constraints, restraints, supports, and everything. Then mass, analyze, and run, and display results. So that's the rough flow of the model generation. You already know that. And this is where the nonlinearity can also come in. So grid system, story, data and geometry, mostly you already know these things from previous ETABS runs, but I just want to summarize that you need to key parameters where the common mistakes can happen. Grid lines, story heights, master story concept, and slab openings, setbacks and podiums, column orientation. You have to be careful if your building has these things, how to model them carefully in the building. So grid lines should match architectural grid lines. Story levels match, column base, fixed or spring, whichever you're using, master story concept, and then similar story where everything is the same. So master story and similar story concept should be used, and story heights and everything should be carefully checked. Section properties, columns, beams, walls, and slabs. So columns, beams, walls, and slabs and floors, you have to define the section properties properly, and then make sure that when you specify that, you specify, because in ETABS, it's very easy to make a mistake when you define a section. If you don't assign the rebar layout, it will automatically assume everything to be column. So many of the beams, if you didn't specify correctly, become column for the design check. So things like that easily can happen. You skip one step and program makes an assumption, and then it makes the wrong assumption. And do not assume that the default values used by ETABS are always correct. They're just defaults. So go through every form and check all the data over there. Beams, T-beam, modifiers, cover, post-tension beam modeling. So everything should be carefully selected. Slab and beam, shell element, thickness and material grade, slab and diaphragm, one-way slab behavior. If you have one-way slab, make sure that you set it as one-way, because otherwise shell element goes both directions. So precast slab, for example, is as a one-way behavior. So you cannot use the conventional shell element, because shell element will go both ways. It will transfer the load both direction, but precast only transfer one direction. So you must explicitly set one direction stiffness or one-way behavior. Things like that are very important. So please read this thing just for you to read. Rigid end zones, meshing, default meshing, and all of them, modeling. So many things are there in ETABS. Unfortunately, every time a new program is released, they add 20, 30 more options, never removing any option. So you can imagine in 25 versions, how many options must have been added to the program. They keep adding more. And the reason is some user calls them up, say, oh, I want to do this one in the program. They add an option. Another company calls them something, they add, and 99% of the other companies don't know why that option was added, because they never asked for it and they never needed it. So a lot of those options exist in the program, which you may not need, you may not understand, but don't choose them if you don't need them or you don't understand them. Start with a simple one before you add things. So this is the offset and intersection point that I was mentioning. Very important. Like, for example, this joint portion. So normally the centerline model will extend to the center to center, but this portion is common. This joint is common between two elements. So if you do not provide these end offsets, then the stiffness will be counted twice, and that's not right. And the length will be wrong. So that's why the joint offsets, these end offsets are very important. Program automatically calculates them now. Previously, we used to input it manually. Now it's done based on the column size and beam depth automatically. But you should check whether it has been done or not. Another thing is offsets. For example, alignment of the beam is, centerline is here, but the actual beam is here. So then you need to shift this point with the insertion point. So insertion point and offsets are very important. So this is the typical example. So if you have a T-beam like this, everything will be modeled at the floor level. So inside the program, the slab will be modeled like that, and beam will be modeled like that, not like this. This is your thinking that you have this one, but if you don't use the offsets, then the program will model it like this inside. Both the slab and the beam will be at the center line of the floor. So which means that you have to then move the slab down by offset and then move the beam down to that level through the offsets. Is the case for column. If you want the wall to be over, the beam to be over there, then you need to, move this one from here to there by using the insertion points and insertion points. Okay. So it's quite common that we miss these. And then we assume if the members to be in the... So remember, the program will not change the modeling. Modeling will still be like this, but it will look like this and will make the correction in the stiffness. Same thing, beam will still remain here like this one, but it will shift the geometry there and make the corrections in the stiffness. So the centerline doesn't shift, just the properties shift. Extrusion, I told you, point to line. You extrude one point and becomes a line. You extrude one line, becomes an area, and then you extrude the area, it becomes a solid. So this is a very good way to create nice models in, especially SAP. ETABS doesn't have extrusion because floors are fixed, but in SAP, you can use extrusion very nicely. You have a nice spiral staircase. You just take one section, spiral, cylindrical extrusion, and you get the whole spiral staircase and so on. So complicated shapes can be generated through extrusion. And this is the typical way. For example, you have this structure like this one. First thing is that you assign fixed or pin supports or hinge or roller, and then you assign the material properties, and then you assign the load. So start with the basic geometry, which is coming from architects. Then you assign your restraints or foundations. Then you assign the stiffness properties, and then you assign the load. So that's the step-by-step things to do. And then after that, those are the menus. And then you draw the grid line, how to create this one. Number 1, grid lines. Number 2, materials. Number 3, sections. Number 4, structure. Number 5, assignments. Number 6, loads. 7, analysis. 8, design. So these are the steps that you will follow. And those are the menus that you need to do that. Then it's about gravity load. So all of this you already know. So just read it and understand it. I don't need to explain. But make sure that you understand all of these areas: shell loads, beam loads, weight, self-weight, live load reduction. This is very important, live load reduction. Often we miss that because it's not possible for the whole building to be, all of the live load to be loaded at the same time. So normally they have many rules on how you reduce the live load, either by story, by area. Different codes have different formula. So for the columns, you have different way to reduce live load. For the beam, different way, and so on. So make sure that live load reduction factors are properly set. For the wind, lateral load, static approach, seismic RSA, response spectrum approach, equivalent lead force, all of these things, you need to specify the loads properly depending upon which code you're using and get the data and so on. So when we have the demos, they will show you.